So let's consider then rotational symmetry. Now, we actually have been through symmetry arguments on a number of different occasions, and we will be following exactly the same outline. You will recall the first step in any kind of a symmetry argument is to think about a change in representation. It's nothing other really than undergoing some kind of a change in how we represent the problem. There's no statement about symmetry at that point, right? The statement comes later when you figure out what the Hamiltonian looks like in the new representation and then say that it must equal the original Hamiltonian. So in this case, our change in representation is really not going to be like a change from position to momentum representation. It's a little bit more akin to the parity symmetry, where we just changed, in that case, the direction of our axes. Again, we will be changing the directions of our axes, but now we're going to be rotating them instead of just flipping the direction of a single axis. So this is really a change in the coordinate system. And I'd like to illustrate to you what that change would look like. So we were going to begin with a typical ordinary XYZ coordinate system, maybe something like so, right? X, Y, and Z. And we want to be very careful, for reasons that will become clear momentarily, that we're always choosing in these constructions proper right-handed coordinate systems. So I've designed things so x cross y, in fact, points in the z direction. So this then is going to be my original coordinate system, but I'm going to change coordinate systems now to a rotated coordinate system. I could make any type of rotation that I like. Because I have spherical symmetry, any rotation should restore things back to their original. I want, however, to think about a particular class of rotations, which will make also our choice of spherical coordinates a little bit more convenient later on. So I want to consider what happens if I rotate my coordinate system about the z-axis. So if I rotate my coordinate system about the z-axis, my new z-axis will point in exactly the same direction. I will call that z prime. The more interesting thing is that my new x and y coordinates are going to be rotated relative to their originals. So the new x coordinate, maybe it will be like so. This will be my new x prime axis, and then my y prime axis would look like thus, right? Where these then are going to have rotated through some angle, and I will call that angle of rotation, for now at least, I will call that theta. So it's really just a rotation here about this z-axis. So that's the first step, is a change in coordinate system. The second step then is to define an operator, an operator that affects that change in coordinate systems. So my operator then I'm going to define is going to be r for rotation, hat to make it an operator, z, because I'm in this case considering rotating around the z-axis, but in general I could have considered rotations about other axes, and the amount of rotation then was theta. And I want this rotation, when applied to any function, because it's an operator, it should be applied to a function, I want that to give me back again what my function looks like in the new coordinate system. So f in terms of these now rotated coordinates, x prime, y prime, and z prime. So to compute then the action of this operator, what I need to do is to figure out what my new coordinates look like in terms of my old coordinates. So I need a coordinate map to compute what this operator actually does. So I have to figure out for any given point x, y, z what the new coordinates x prime, y prime, and z prime will look like. Now, because nothing's happened between the z and z prime axes, at least that one's pretty simple. The z coordinate will stay the same. All of the interesting action then happens among the x and y coordinates. So I'd like to draw a top-down view, a two-dimensional diagram, to make this a little easier. So I'm now going to be transformed into this new coordinate system, x prime and y prime, like so. So this is going to be a top-down view, looking down along the z-axis. and then my original axes, right, are an angle theta sort of backwards from these. So the x-axis then would look something like so, where this here is angle theta, and the y-axis then would look like this, like so, where this again here is the same angle theta, so that both of these coordinate systems have a nice right angle associated with them. And so now my job is to figure out, if I had coordinates x, y in the xy plane, what it would look like in the x prime, y prime plane. And I'm sure you all have done this type of coordinate rotation before. So here's a quick shorthand for making sure you write down things properly. So the easiest way to do this is to think about what happens first to a point on the x-axis, and then figure out what happens to a point on the y-axis. And if you get those 2 points correct, then you will actually be able to get the transformation for any point in general. So if we had started along the actual x-axis, that point here would be at a distance x along this axis. And then if this here is my distance x, I can readily compute the coordinates of where this point ends up in the x prime, y prime coordinate system. So the x prime coordinate, because I can make a nice right angle here, would be this length x times the cosine of the angle theta, because that's the adjacent side. So I get x cosine theta. And it will now also have a y coordinate, which will be a y prime coordinate, I should say, which will now be negative. And the amount downward will be sine theta times the distance x. So that will be minus x times sine of theta. That takes care of a point along the x-axis. If I look for a point along the y-axis, its x prime value now picks up a positive amount, which again will be this distance now, my distance y, along that original axis, times then the sine of theta, because this is the opposite side. So then that would pick up then a plus y times sine theta. So a general point then would have an x and a y. It would end up being the sum of these two. And then likewise for the y prime coordinate, that would be again this hypotenuse times cosine theta, because this is the adjacent side. So this would then become plus y times cosine theta. So therefore, now that I know what things look like in these new coordinates, I know what the action of my operator is. The rotation operator of an angle theta about the z-axis, acting on my original function f of x, y, and z, gives me the same function but evaluated at a new point, which is x cosine theta plus y sine theta. And then in the second coordinate, it will become y cosine theta, just writing it, a little bit in backwards to emphasize the y coordinate in the second location, x times sine theta, comma, then z. Now, this would give me the answer for a general angle theta. One of the very nice things about rotations is that rotations have a continuous set of values theta. It's not like the parity operator where you apply it once and then boom, you've got your answer, right? For rotations, I could apply the rotation all at once, or I could just rotate very slowly with a bunch of small, tiny, infinitesimal rotations, which I know will eventually add up to my larger finite rotation. So I won't be losing anything if I decide instead to focus on very small or so-called infinitesimal rotations. So we want to really focus on that, infinitesimal rotations. The advantage of going to the infinitesimal rotations, as you will see, is it will actually make the math a lot easier to think about in terms of what this actually is doing to my function. And as I said, I don't lose anything because ultimately I can build up a finite rotation by applying a large number of these infinitesimal rotations. Now, when I'm strictly mathematically speaking, when I'm talking about infinitesimal rotations, that means I'm computing things, compute everything up to first order in theta. I'm going to neglect terms that are higher order, neglect terms that are what we call order of theta squared. Now, if I do that, you can begin to see what will happen to my function. Because the cosine function, cosine of theta, is, if I power series expand it, it's 1 minus theta squared on 2 plus dot, dot, dot. The sine function is theta, actually, in the small angle approximation, but there's higher order terms. Theta cubed on 3 factorial, which would be 6, plus blah, blah, blah. Higher order terms. If I'm only computing things out to second order and neglecting things of order theta squared, I can neglect this term, and I can neglect this term here, right? And I know I'm making only errors at order theta squared. So the very nice thing about this, notice then, is that the cosines that I have here will become just 1. So I can eliminate those. And the sine thetas just become theta. So I can just, if you want, scratch out the sine theta to at least, again, this order. Now, continuing along with this idea, so I'm looking at a small rotation on my function f. The result of this then is f evaluated at essentially the original point, x, plus, though, a small change, and the amount of change is just the small angle theta times y, so x plus theta y. The y coordinate, again, is mostly intact. It's just the original y value, but now minus a small amount, minus this small angle theta times the x coordinate, it turns out, comma z. Now we're ready to make some progress, because this itself, we realize, is going to be very nicely and well approximated by the original function itself, right? There's essentially no change in the function when I make a small rotation, at least at lowest order. But to first order, there are some changes, right? We know the rate of change of f with respect to its x-coordinate, so there will be a term that goes like d by dx of f, right? I'm just Taylor series expanding this thing, times the small change in the x-coordinate, which is actually theta times y, plus then also there's this change, and the rate of change of f with respect to y is known as partial f, partial y, and that's then multiplying this small amount of change, which is minus theta x. And of course, there's no contribution, no changes coming from the z-coordinate. And notice I've stopped my Taylor series of f out at the first order, so there will be additional errors in this, but those errors, just like the errors in these coordinates, are all going to be order of theta squared or higher. So I'm doing my job and just considering what happens for small angles theta to lowest order. Now, what the expression that we have here, you will notice, I really want to get it all in terms of some operator that's applied to f. And I really do have some mathematical operation. I have to take some derivatives of f, multiply them by some numbers, and then add it back to f again. And I can gather all of this into what looks like a single operation by factoring out f, like so, and accounting for all of the terms. So the first term I have is just f, right? So that's just a 1. Times f would give me the f back again. Then I have these angle theta terms. And so let's see, well, let's look at this term here first. It starts with x. I kind of like x. I'm kind of biased towards x. So it's going to be minus theta. And what theta itself is multiplying is x times the y derivative. So that's x times d by dy. And then I've got this term here, which enters with a plus sign, but I factored out a minus, so that would be a second minus to make a net plus. I've got the theta factored out, but what's left here is y times the derivative with respect to x. So then I know, therefore, I have a nice expression then for this rotation operator. Apparently it's the identity operator minus theta times this interesting combination, x times d by dy minus y times d by dx. And of course, all of this is always plus higher order terms that we're not considering at the moment that are negligible when theta is very small. Now, so much for the rotation, right? That is the rotation operator. And we could certainly derive the rotation operators for the other various axes. To make progress on this, though, I want to begin to connect it back to the physics of the system. And our connection to physics in terms of these operators is to recognize, okay, I know for sure, right, this is the operator that goes with x, and this is certainly the operator that goes with y, so that's y hat. The other interesting thing is this operator is almost exactly the operator for the momentum in the y direction, right? The momentum in the y direction, the operator for that is h divided by I times d by dy. So if I invert that relation, that tells me d by dy is the inverse of that. It would be I over h bar times the momentum in the y direction. Likewise, derivative with respect to x is just I over h bar times the momentum operator for the x direction. And this way, we're making contact with the physics. And if you want a quick reminder to know how we could see that so quickly, remember the momentum in the x direction is h on I times d by dx. And all I've done is just move h on I to the other side of the equation. Now we're really getting things nicely in terms of physical operators. Let's look at this a little more closely. I've got this factor of minus, right? I'm trying to gather all my factors. I have a factor of I divided by h bar times O, right? That's all these factors that I've accounted for, I on h bar with the O's. But then I have this very intriguing combination. I've got x hat p hat y minus y hat p hat x. Now that combination should look very familiar to us. This feels like some object that we recognize from classical physics. We haven't seen it before in our quantum class, but this should look very familiar, right? It's got something like distance times momentum, but it's got this scrambling of coordinates and minus signs that feels a whole lot like some kind of a cross product. And in fact, if I look at the cross product, I hat, j hat, k hat, between my coordinate location, x, y, and z, and my momenta, px, py, and pz, I can get exactly this cofactor determinant, x times py minus y times px, which is what I see here, and that cofactor would come from the k hat component of this cross product. So this, mathematically speaking, is the cross product between my location vector r, that's my xyz, and my momentum vector p, and that I hope you all recognize as the angular momentum vector. So this combination evidently is the operator now, because these are all operators associated with the angular momentum in the z direction. So if I want to turn this then really into a proper operator equation, that's easy enough to do. These all would become my operators, just as you see, and then I have my, complete standard definition. So the bottom line lesson here, and this is critically important for us, is that if I want to create, or what we call generate, a small rotation for a small angle. So let me actually call my angle epsilon now to indicate that this is small, right? Rotations by small angles around the z-axis are, if you will, generated by this interesting combination. It's I, the z component of the angular momentum operator, times the angle theta divided by h bar. So in words, the lesson is that the angular momentum is the generator, we call it, the generator of infinitesimal rotations. And this is a key result, so I'm going to put a box around it. But before I complete my box, the last observation that I would like to make with you is that, well, notice I just happened to pick the z-axis, right? I just picked the z-axis. I could have physically done this type of rotation and pick the same actual axis, but have relabeled, if you will, my coordinate system, so that even though I was doing exactly this rotation, if I had relabeled this coordinate system, I might have thought I was doing the rotation around the y-axis or around the x-axis. And if I had done that, right, clearly what I would have pulled out, because the answers that I get really shouldn't depend upon my particular choice of coordinate system. I would also have learned then that if I had done the rotation around what I had called the y-axis, I would have gotten exactly the same formula, except now, of course, it would be the y component of the momentum that generates those rotations, and likewise also for the x rotation. The other thing that I hope you see from this argument is the importance of choosing the proper right-handed coordinate system. Right? This would not have worked if I had chosen a left-handed coordinate system, because it all depended upon the cross product giving me the angular momentum, which action of that cross product depends upon us being in our right-handed coordinate system. Now I notice here I do have a small typo. I was doing rotations at angles epsilon, and I had written my angle theta. So I'll just put the epsilon here. By putting the epsilon, what I'm really saying is I don't have to keep writing this plus order theta squared. So now we have these infinitesimal generators of our rotations.